Hello friends, welcome back to the lecture series on applied statistics and econometrics. So, in this lecture we are going to continue our discussion with multiple linear regression models. So, before we visit the models and analysis, let us have a look at today's agenda items. So, in this lecture we are going to extend the classical linear regression model that we have seen in the previous lecture by adding one more assumption, and we are also now going to express our model in matrix notation, because we are going to involve more than 3 explanatory variables. So, the next item in the list is a very important theoretical result known as Gauss-Markov theorem, and then we are going to revisit the goodness of fit measures. We have already done goodness of fit measures discussion, but we are going to extend the analysis here, and finally we are going to talk about outliers and influential observation detection. So, if you remember, a linear regression model has one simple objective, and that is to find out the statistical dependence between one dependent variable or response variable and a set of independent variables or regressors, and the relationship has to be linear in nature. So, here in this slide I am going to provide you a brief recap of multiple linear regression. So, we are going to start the slide with the concept of population regression function, and that is given by this expectation formula, expected value of y given the variables x1 to xk, and that assumes a linear functional form beta naught, the intercept term, plus beta 1 times x1 dot 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 beta k times xk. Now, it is very difficult to look at the multiple linear regression model, because it is a k dimensional problem. So, if I want to now tell you the multiple regression story in a nutshell, let us reduce the dimension of the problem and let us work with only 2 explanatory variables. So, here let us take an example from microeconomic theory. So, let us focus on butter consumption for the matter, and that is our y variable. Well, we take logarithm of butter consumption data. So, that is basically my y variable, and then I assume that my butter consumption depends on the log of price of butter, which is denoted by x1 variable, and log of price of margarine, and that is my x2 variable. Okay. So, my linear regression model will be y I equals to beta naught plus beta 1 x1 I plus beta 2 x2 I, where all the variables y, x1 and x2 are in logarithm form. Okay. So, now suppose I got a data set and I estimated the regression coefficients, and then I can now draw the fitted lines. Note that in this case, as we are dealing with more than one explanatory variable, actually we get a surface or a plane, and that is drawn in this 3 dimensional diagram, where y actually is the vertical axis, and that is measuring this log of butter consumption, and then I have 2 x axes, one for the log of price of butter and the other one is for log of price of margarine. Okay. Now, you see here what I can infer from the diagram is the statistical dependence between these 3 variables. So, let us now first talk about the variable y and x1. So, that is the log of butter consumption and the log of price of butter. So, here if you look at the slide, then you will see, if I take a cross section of this diagram in the y x1 plane, then there is a downward sloping straight line, and that is because here I am observing the demand function for the butter. So, as price of the commodity increases, quantity demanded shall decrease, that is coming from the law of demand, and that is why I am observing downward sloping straight line here. But now if I take a cross section of this surface or plane, and if I now look at a two dimensional plot where I am measuring y along the vertical axis and x2 as the horizontal axis, then I see that there is a positive relationship between these two variables x2 and y. Why is this so? You do not have to assume microeconomic theory here, think from the logical perspective of a consumer. So, here margarine and butter, these are substitute commodities, right. So, if price of one commodity increases, then of course, the commodity demand for the other good will increase. So, if price of margarine is going to increase, then you can expect that demand for butter will go up, and that is why the variables y and x2, they are showing a positive relationship in the y x2 plane. Now, regression is not only about looking at the slope and noting down the nature of the relationship between two variables. Regression is also about quantifying the strength of the relationship, and also after getting the direction of the behavior of two variables, the measurement that okay, if there is a change in one variable by 1 unit, then how the other variable is going to change, by how many units it is going to change. So, here as we are dealing here with a log model, here the elasticities have very nice interpretation, and the slope coefficients beta 1 and beta 2, they can be called the elasticity. And here if you look at the diagram again, the beta 1 actually gives me own price elasticity. So, that means that if there is 1% change in the price of butter, how many percentage of change in butter consumption I am going to expect. And beta 2 gives me a measure of cross price elasticity. So, it tells me that if there is a 1% change in price of the margarine, then by what percent my butter consumption is expected to change. And note that this cross price elasticity theoretically can two types of values, positive and negative. So, here as we are dealing with a substitute commodity like margarine, we are going to expect a positive number for beta 2. So, before we end the discussion on this brief recap on multiple linear regression models, let me take you back to the slide once more, as I want to mention a very interesting point. So, now let us consider this diagram again, and here you see that actually I do not have a straight line in two dimensional plane as my regression equation. Actually I get what can be called a regression surface, and that is colored in green. So, all my fitted values from the regression equation will lie on this regression surface. But note that the original observations on x1, x2 and y are such that the observed bundle x1, x2 and y, that point may not lie on that surface. So, that kind of a point is denoted by this yellow circle here. So, how do I measure the fitted residual value or the estimate of the error from my regression equation? So, I need to now calculate the distance of this white color ball or circle from the point that actually I observe for my values of x1 and x2 on this particular surface. So, this distance is given by this broken line. Okay. So, now we are going to revisit that classical linear regression model, the theory part of it, and we are going to augment that theoretical discussion with one additional assumption, and that is the assumption of normality. But before I introduce the assumption of normality in this theoretical setup, let me again remind you that we start with a population regression function, and then we get the stochastic version of it, and then basically we have to estimate the unknown values of population parameters. So, that is basically the crux of the classical linear regression model. So, we start with the formal assumption number 1, which says that a linear regression model specifies a linear relationship between y and k number of explanatory variables, and then the population regression equation now can be written in matrix notation in much compact form, and that is written as y equals to x times beta plus epsilon, and that can be further rewritten as expectation of y given x plus epsilon. And now I am going to explain you what are these different components that you see in this equation. So, let us look at the right hand side variable. So, that is basically my y. Now, last time when I wrote the linear regression equation, I was mentioning individual values, and that is why I had this subscript I after the dependent variables nomenclature y, but now I have only y, and that is basically giving me a column vector of the regression. So, the dimension of this column vector is capital N times 1. So, there are n number of observations in this column vector. So, n is basically my sample size. Okay. Now, let us focus on capital X. So, capital X is n cross k regressor matrix. So, what do we mean by here? So, capital K is basically small k plus 1. Why small k? Of course, we are assuming there are k number of explanatory variables. K is an arbitrary number and it will change from one example to the other, one case to the other, and why we have to add 1 to it, because we have to have the intercept term, right. So, for the intercept actually we have to now add one column in this data matrix, and this column will have all ones for this n number of observations. So, that is why capital K will be equal to small k plus 1. So, the next in the list is the regression coefficient vector, and that is the beta vector. So, that is capital K cross 1 column vector again, and then we have the expected value of y given x, and that is capital X times beta. So, that is capital N cross 1 population regression function, and finally epsilon is basically the difference between the observed value vector y. So, epsilon is basically the difference between the observed value y and the expected value of y given x, and that is also again n cross 1 vector, that is also called error vector. So, now note that this n cross k matrix is also called a data matrix, and this is a matrix of observed sample values of the regressors x I naught, x I 1 dot 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 x I k. So, x I naught is basically that column which will have values 1 for all observations. So, this is inserted in the data matrix to take care of the intercept term. Okay. And the remaining small k number of regressors are basically the explanatory variables. Now, if you remember the last discussion, you can have square terms or cube terms of existing explanatory variables in the same data matrix. Okay, so next we focus on the assumption 2, and that is simple. It says there are no exact linear relationships between the variables. So, it rules out the case of strong multicollinearity. So, if you remember, I discussed the case of multicollinearity previously, and that says that no two explanatory variables should be perfectly linearly correlated. So, the product moment Pearson correlation coefficient between two explanatory variables should not be exactly equal to 1. Actually, it should not be greater than 0.9, because then you are going to see a very strong linear relationship between two explanatory variables. Later part of the course, we are going to revisit this idea or concept of multicollinearity, and we are also going to talk about some remedies. Now, we move on to assumption 3, which says that errors are purely random draws from some population and no observation on x convey information about the expected value of the error. So, what does that mean? So, that says that your expected value of epsilon given x is equal to 0, and this is popularly called the exogeneity assumption. So, that means that there is no covariance or correlation between the error variable epsilon and the explanatory variable, any one of the explanatory variables that you have in the data matrix. Okay, so now before we start talking about the normality assumption, let me remind you about assumption 4 and 5. I have not written assumptions 4 and 5 in this slide because I believe that you remember them from the previous discussion. Can you tell me what are they? So, they are actually the assumptions of homoscedasticity and 0 serial correlation. So, what is homoscedasticity? Let me remind you briefly. So, here we assume that the variance of the error term will not change with respect to the x values. So, it is constant over the data set that you have. So, the variance of epsilon is equal to sigma square, you can say in the language term. So, in assumption 5 we know what do we mean. In mathematical statistics term we say that covariance between epsilon I and epsilon j is equal to 0 when I is not equal to j. So, that means that if you take any two values of the error terms, they are not correlated with each other. Finally, we start with the assumption of normality, and let me tell you one thing, this assumption number 6 which is talking about the normality is not required to conduct a classical linear regression model. So, if you remember 2 lectures back only we have derived the OLS estimators and for that matter we did not assume normality anywhere. And if you also remember in the first module of the course when we did curve fitting by least squares principle, there also we did not assume normality. So, why we have to now introduce another assumption on normality? You will see later on we are going to conduct hypothesis testing, and for hypothesis testing we need to assume certain distributional assumptions, and that is why we are bringing normality in the picture. There is also another reason. If you remember we also spoke about another estimation method which is called the maximum likelihood estimation method, and for that you have to make some distributional assumption as well. So, we are here seeing the OLS principle, how it is applied to find the estimates of the regression coefficients of a classical linear regression model, but one can also adopt the maximum likelihood estimation method MLE, and for that you have to assume some distributional form for the errors, and that is why normality assumptions comes handy, and people make normality assumptions in the context of classical linear regression model. So, here we say that my error vector epsilon has a multivariate normal distribution. Why it is a multivariate normal distribution? Because here you are dealing with n number of observations. So, basically in that error vector you have n items epsilon 1 to epsilon n. Now, I am assuming that each one of these vector components like epsilon 1, epsilon 2, epsilon 3 dot 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 epsilon n, they are all random variables, right. So, basically there are n number of random variables. So, if you bring in the concept of normality, then you have to bring in the concept of multivariate normality. So, here I assume that epsilon follows a multivariate normal distribution with mean expected value of epsilon given x, the data matrix, is equal to a vector of 0. Why it is a vector of 0? Because here I am not talking about one particular random variable, I am talking about n number of random variables together. So, this 0 underscore is the n cross 1 vector of zeros, and this multivariate normal distribution will have variance which is given by expected value of epsilon epsilon transpose or epsilon epsilon prime given the data matrix X, and that will finally take the form of sigma square times I n, where sigma square is the constant variance and I n is basically n cross n identity matrix. So, if you remember your matrix algebra lessons from school or college, then you can actually have a picture in front of your eyes now. So, I n is basically identity matrix where the diagonal elements are all ones and the off diagonal elements are all 0. So, basically you just have to multiply a constant sigma square in front of that I n matrix, and that will give you the variance matrix for the epsilon. So, in a compact form we can say that error normality assumption results in this expression: epsilon given data matrix X follows normal with mean vector of 0 and then sigma square I n covariance. So, the sigma square I n is basically a variance covariance matrix where the covariance items are all 0 because of the assumption of 0 serial correlation. So, only the variance terms are going to stay in that variance covariance matrix, but actually in general this variance expression that we have written in terms of V of epsilon given X, that is basically a variance covariance matrix, because later on in the course we will relax these assumptions and then we will see that these off diagonal elements can be replaced by certain statistical measures, and these are all covariance measures, and wait for some time to see that complicated picture. Now, what is the implication of this normality assumption if we introduce it in the classical linear regression model? Well, if you remember, when we discussed the case of normal distribution, we spoke about the linearity property of normal distributions. So, let me remind you again if you have forgotten. So, any linear function of a normally distributed random variable is itself normally distributed. So, if I take simple variable x which follows normal distribution, and if I now take transformed variable y equals to alpha plus beta times x, where y is another continuous variable. So, here y will also follow the normal distribution. That is what basically linearity property of normal distribution says. So, here in the classical linear regression model context, as u is normally distributed by assumption and y is a linear function of u by assumption, the regression vector y has an n-variate normal distribution, and this normal distribution or multivariate normal distribution will have a conditional mean vector, and that is given by expected value of y given x equal to x times beta, and conditional covariance variance covariance matrix given by V y given x the data matrix, and that is equal to sigma square times the identity matrix of nth order. So, then what to do? If you remember, next step would be to apply the least squares principle and get the estimates of the slope coefficient and the intercept coefficients, and here as you have k number of explanatory variables, it is indeed very difficult to even apply Cramer's rule. Cramer's rule will save you up to say 3 explanatory variables, but not more than that. After that it is going to be extremely clumsy. So, what is the remedy? And you have no other remedy but to apply matrix algebra. So, if you now apply matrix algebra, the process of taking derivatives to minimize the error sum of squares is extremely messy, and it is too theoretical. So, I am going to skip all these steps, but I am going to show you the final outcome, because if you remember, then that will become very handy. So, here I am going to show you the final expression that comes out of the sum of square error residuals minimization exercise, and that coefficient vector B is given by this matrix formula x transpose x inverse x transpose y. So, here this capital T is denoting transpose, but note that in many textbooks you can see the use of dash to denote transpose. I am not going to show you any example here to help you with matrix transpose and inverse and all, because I have set the prerequisite for the course, and I am assuming that you have some knowledge of matrix algebra at high school level. So, there you should have done matrix inversion and taking transpose of a matrix and all. So, I request you to consult some of the previous study materials on matrix algebra. Okay, so once the coefficient vector B is estimated, are we done? The answer is no, we are not done. Why? Because when you are writing your classical linear regression model, then there is another population parameter that you have written. Many times I see that students forget about this population parameter when I give them a data set and ask them to compute the values of the coefficients and the unknown population parameters. They think that the unknown population parameters are only the coefficients that are there in the regression equation, but how can you forget that epsilon, which actually follows some distribution. I mean, here in this lecture I have introduced the concept of normal distribution, that is an assumption, but you do not have to assume normality. It can follow any arbitrary distribution with 0 mean and constant variance, but that unknown constant variance is also a population parameter. So, you have to get a proxy or an estimate for that as well. So, when I am saying that you have to get the estimates of your classical linear regression model or classical normal linear regression model, do not forget to get the value of the sigma square hat or the estimate for sigma square, the unknown population error variance. So, here the estimator of the constant error variance sigma square can be obtained by dividing the estimated SSE, the sum of square errors, and that is given by transpose E by its degrees of freedom capital N minus k. Now, what do I mean by this expression E transpose E? So, here E is basically the sample residual, right. So, epsilon is basically an error which is a population concept, and when you get a data set you apply OLS least squares principles or maximum likelihood whatever estimation principle to the data set, and you derive the values of these slope coefficients and the intercept coefficients, and then you generate the residuals from the regression, which is basically E equals to y minus y hat. So, y hat is basically the fitted value that comes from the regression equation that you have just estimated. So, that E now you can make use of to get the estimator for the unknown population error variance, and you have to basically take that residual, square it, and then sum that squared residual for all n number of observations, and that is basically this E transpose E is giving you in the matrix form. And this is basically just a scalar number, and you have to divide this by its degrees of freedom capital N minus k. Why we have to divide by the degrees of freedom and that is n minus k? Note that you start with n number of observations in the data set and then you apply your OLS technique to it, and how many unknown parameters you are estimating from the model before you actually try to find an estimator for this unknown population error variance. You have to get k number of explanatory variables corresponding slope coefficients, and then there is also an intercept coefficient. So, small k plus 1 equal to k. So, you have to actually calculate or derive the guess estimates or proxy values for these many unknown population parameters before you actually take up the task of finding an estimator for the unknown population error variance. Hence, you need to divide this sum of squares error residuals by capital N minus k, which is basically the number of observations which are independently left to the sample. Okay, now we are going to talk about a very important theorem, and that is called Gauss-Markov theorem. Now, before I state it formally from slide, let me tell you why we require this theoretical result. Well, we have got our OLS estimators for the intercept coefficient, the slope coefficient and the population error variance. But we have to now judge how good or bad they are. Now, what do I mean by that? So, if I say that some estimator formula is good, then it should obey certain properties. So, the Gauss-Markov theorem actually talks about certain properties of the OLS estimators. So, here we say that if the first 5 assumptions of the classical linear regression model are holding, then the OLS estimators have the smallest variance of all linear and unbiased estimators of population regression parameters. And if this Gauss-Markov theorem holds, then we say that the OLS estimators are blue, and by blue I mean best linear unbiased estimator. So, now I will have 3 notes that are related to this Gauss-Markov theorem. Note that this theorem does not say that this beta naught, beta 1, beta 2 and other estimators of unknown population parameters are best of all possible estimators that you can theoretically propose. They are best when compared to similar estimators. So, what do we mean by similar? So, the estimator has to be first unbiased, and then it has to be linear. Now, we all understand what do we mean by unbiasedness and the linear estimator. So, I am skipping that discussion. Now, out of this special class of estimators which are unbiased and linear in nature, then what will make them so special that we will call them the best. So, it can be shown that these OLS estimators have the minimum variance out of all linear and unbiased estimators in this context, and hence OLS estimators are called blue. So, note that in this Gauss-Markov theorem also we have not made use of the normality assumption, which is the 6th assumption that we made in this lecture. Once we conduct OLS regression technique, and when we get the values of the unknown population parameters, then we can get the fitted values, and of course one can try to draw a scatter plot, and there in one axis the person can plot the actual observed values of y, and on the other axis one can plot the fitted values of y hat. Okay. And if the scatter plot is showing that points are close of each another, then you can say that okay, the fit is good. But there could be some cases where you see that there is huge deviance between the fitted value y hat and the actually observed value y. So, basically we are talking about high residuals in these cases, right. So, we should not stop after getting linear regression equation which is given by the OLS. We should also look at the fit of our regression model, and the first way to look at the regression diagnostic checking is by looking at the outlier. So, if there is an outlier or not, there could be difference between the fitted value and the actual value, but the gap should not be very high. If the gap is very high, then there could be actually some issue of outliers. And in the next slide we are going to discuss outlier detection and all, and this is very handy for applied economic and statistical research. So, what is an outlier? Formally we can define an outlier as a point that has a larger or smaller y value that the model would suggest. Now, of course, this is in a relative sense, of course, and this can be due to two different reasons mostly, and number one reason could be that there is a genuine large error, and the otherwise there could be some typographical errors in data entry process and all. But we do not know a priori what is the reason what has generated that outlier. Now, there are multiple techniques, statistical techniques that are available in a statistician's toolkit to detect outliers. We do not have time to go through all of them, we are only going to concentrate on one particular measure. So, here in this course we are going to focus on the standardized residual as the measure for outlier detection, and this is defined as the quotient resulting from a division of the raw value of the residual by an estimate of the root mean square error, that is basically the standard deviation of residuals. So, once you generated the values of residuals, that is basically a variable. So, you can also compute the standard deviation of that variable. So, that is basically the root mean square error. As we have introduced the assumption of normality in this lecture, so we can now feel free to assume normality, and by the assumption of normality we can say that 95% of these standardized residuals should be between -2 and +2, and 99% should be between -3 and +3. So, if we find an observation with a standardized residual value above 3 or below -3, then it can be considered as an outlier. Now, outlier is also related with a concept which is called leverage. What is leverage? We are not going to get into details of this concept leverage, because they are not actually that much used in the field of econometrics, but as they are heavily used in the field of applied statistics, I am going to briefly introduce this concept here, and I will just give you some brief idea how leverage and outlier can actually interact with each other. So, formally speaking, a high leverage point is a point with extreme values of the explanatory variables, and how to detect leverage from the regression exercise. There are again different measures, but we are only going to talk about one particular measure. But note that all these different measures that are available there to find out leverage, they follow one principle, and that is called leave one out principle. So, what do I mean by leave one out principle? So, here I am going to focus on one particular measure, and I am going to explain you this leave one out principle. So, basically what you have to do, you have to rerun your regression model several times. So, suppose you have capital N number of observations. So, you are interested to find the leverage of the small nth observation. So, you actually have to now leave it from the sample. So, you have to exclude it from the sample, and then basically you have to run the regression, and if you are now interested on n plus 1th data point, then you have to bring nth observation back in the sample, and you have to exclude n plus 1th sample out from the sample, and then you have to run the regression again. So, this is the way you have to run multiple times of regression analysis, but let us look at the measure. We are only going to concentrate on the simplest possible measure. So, here the measure is called DEFITS, and the full form is standardized difference in fitted values. So, that is defined as the difference of actually fitted value, which is y hat I, that comes from my original regression, and the fitted value for that particular observation. So, here the DEFITS is defined as the difference between y hat I and y hat I given minus I. So, I have to exclude that observation I from the sample, and then I have to run the regression. I have to get the coefficients, and then if I apply those coefficients from the second regression, I will get again a value of y hat I, or the fitted value for the ith observation, and I am talking about that difference, and that difference should be divided by the standard error of y hat I, which comes from the original regression. So, how to detect a problem? So, here if for any observation I see that defects take value greater than 3 times square root of k divided by n minus k in absolute terms, then there is a problem. Now, in the last part of this slide, I am going to talk about the linkage between leverage and the outlier. So, let us first look at a high leverage outlier. What is a high leverage outlier? So, it can actually affect the fitted plane and distorts the fit sometimes extremely, and in extreme cases it may not have a big residual value, but as the leverage is very high for that particular observation from the explanatory variable side, there could be problem, and in extreme cases it can increase the R square value, but that is rarely the case. Now, what is the low leverage outlier? So, in that case we see that that observation does not distort the fit to some extent. Usually it has big residual and it inflates the standard errors. So, it decreases the R square value. Now, note that here I actually have given you very simple introduction to leverage. If we really want to explore the interaction between leverage and the outlier, then it will take up a full class, and that is not the objective of the course also. So, I end here at this point. I let me move on to the other concepts which are much more relevant for econometrics. So, we again visit the concept of goodness of fit as the model diagnostic issue. We have already seen this goodness of fit previously, but let me repeat this again, because now we have a multiple linear regression model case. So, I will start with that decomposition of the variance thing that we have done in ANOVA, but I will first start with the simple identity which has this y I equal to y hat I plus the regression residual. So, to have an idea about the goodness of fit issue, you concentrate on the first red box that is given on the northwest corner of this slide. So, here you see that I have actually expressed the total variation in the explanatory variable that is split in two components, and first component is the variation that is captured by the model, and that is y hat I minus y bar, and then there is of course a residual or error which is y I minus y hat I. Okay. Now, that equation can be used to write another equation or expression. Now, this time we have to make use of the sum of squares concept. So, you just square these differences, and then you sum over all observations, and then you get the first component here, and that is basically sum of squares of the difference between the actual observation value for ith observation and the grand mean y bar that is there in the sample. Okay. So, that is called the total variation. So, that is basically one component of the sample variance formula that we have dealt with previously. Okay. Now, that is now divided into two further components. Okay. And first component is basically the model component. So, that is basically called the sum of squares regression or sum of squares model, and the second component is basically called the sum of squares residual or sum of square error. Now R square, the coefficient of determination or multiple coefficient of determination, as we are in the multiple linear regression lecture, that we have defined previously, and that is basically defined as the SSR divided by SST, or 1 minus SSE divided by SST, and that measures how much a model explains the overall variation of y. So, let us quickly have a recap of this multiple coefficient of determination concept. So, here I am showing you a Venn diagram. So, here I have 3 circles. So, this is a simplified case, of course. So, I have one y, the dependent variable, and I have 2 x's, explanatory variables x1 and x2, and note that both x1 and x2 explains some bit of variation of y, and actually these 2 circles x1 and x2, they are variations, have some common part, and all these 3 circles intersect with each other. So, here you see that there are intersections of these 3 circles, and there are common areas in this Venn diagram. So, this common area, which is given by the x, which is given by the black color, that basically is the common contribution of x1 and x2 variables variation in explaining the variation of y. But there is also another component, which is basically an intersection of the x2 circle and the y circle, that is in light blue color, that also contributes to the R square computation. So, basically what is left, and that left area is basically colored in gray, and let us have a look at it. So, here the part of the y circle. So, this circle gives you the total variation of y, right. So, this area which is colored in gray, that part is actually not explained by x1 and x2, the explanatory variable. So, this is the unpredicted or unexplained variation in y, and that gives me the 1 minus R square area. Let us have some brief discussion of R square. So, you see, as we are dealing with k number of explanatory variables, addition of any regressor always increases R square value regardless of its relevance to the explanatory variables, relevance to the variation of the dependent variable. Now, does it mean that as addition of explanatory variables will not decrease my R square value? In fact, in all probability it is going to increase the R square value, and we know that higher R square value is good for my model fit. I can say my model is performing better. Shall I keep on adding more and more explanatory variables in the linear regression equation? No, not really. Actually, there is a trade off between the parsimony or the simplicity of a regression model and this goodness of fit. I mean, you can have more explanatory variables and jack up the R square or the multiple coefficient of determination value, but that will come at the expense of the simplicity or the parsimony of the model. Note that when you are conducting a regression analysis, just think from a policy perspective or a practical perspective. Say a farm manager wants to do something with the regression equation that you have estimated, or a policy maker wants to frame a policy or decide about a very serious policy issue by looking at the regression equation that you have reported to the authority. Now, if you actually have a 27 variable regression model or very complicated functional forms involving square, cube, log, square root and what not, then that messy model, that complicated model will be of not much help to the person who is actually going going to use the model, or who was willing to use your model. So, from the practical standpoint, there has to be a limit up to which you can add variables in your linear regression model. So, where to stop, that is the question. Now, there is a measure provided by statisticians. Actually, there are multiple measures, not one, but related to R square there is only one measure that is proposed by statisticians, which will help you to identify where you can stop. So, this adjusted R square measure takes care of or addresses this trade off between the fit of the model and the simplicity of the model. So, this concept adjusted R square gives the penalty for adding extra regressors. So, it adjusts the original R square concept with the number of independent variables in the model, and it only improves when the new variable added improvement to the fit of the model. So, basically what happens, suppose you have one particular variable that is coming to your mind, and the question is that whether you want to add in the regression equation or not. And if you add in the regression equation, probably it will give you a higher R square value, maybe marginally high, but then the question is that will you keep that variable in the regression equation? You have to judge by looking at the adjusted R square, because adjusted R square actually now charges you a penalty for throwing an additional explanatory variable in the regression equation and make it further complicated. Okay. So, if the adjusted R square value goes up by incorporating this additional variable, then you should keep that variable in the model. So, now let us look at the formula of the adjusted R square. It is little bit complicated compared to the original R square formula. So, it is given by 1 minus capital N minus 1 divided by capital N minus k, and this is whole multiplied by 1 minus the original R square. So, many softwares routinely report this adjusted R square. You do not have to even ask the software to calculate it separately. So, the best way to go for a model selection is not by looking at the value of the R square. You should look at the value of the adjusted R square. So, you keep on adding variables in the model as you see that adjusted R square is increasing, but you stop when you do not see any improvement in the adjusted R square measure after throwing an additional variable in the regression equation. So, now we are going to look at the final measure of the goodness of fit, and that is called the Akai-K information criteria. So, in the Akai-K information criteria, what happens? We still make use of the sum of square error residuals as we make use of it in the R square formula. So, that is why you see that E transpose E is given in the formula, and that is basically giving me the measure of misfit in my model, the measurement of deviation in the model. And of course, I expect that as I introduce more number of explanatory variables in my regression model, this E transpose E number will come down. So, that is good for you, but actually you have to now charge the penalty for adding this explanatory variable, because you are sacrificing the simplicity or the parsimony of the model. So, you have to add the penalty component. And if you now look at the second component of this formula, which is 2k divided by n. So, that is basically the penalty component in the formula. So, as you throw more and more explanatory variables in the linear regression equation, E transpose E falls, but then although the first component is overall falling, the second component actually is rising, because 2 and n are fixed numbers. So, if you throw or add more and more regressors in the regression equations, k will increase. So, the second component of the formula will increase. So, you see here one component is falling and then the other component is rising. So, there has to be balance to strike, and generally what happens, you go for model selection using AIC when you go for the minimum AIC criteria. Okay. So, this is the end of today's lecture. In the next lecture, we are going to introduce the case of hypothesis testing in the context of multiple linear regression model. See you then. Thank you.